Hiya. We are still trying to finish up chapter 2. We're going to talk a little bit about a bridge into chapter 3 today, getting us closer to the topic of determinants. But of course, you know, you've started with chapter 4.1. So we are going to be able to use a lot more tools than the book does in chapter 2. Okay. So lemma 11, so you've had lemmas 1 through 10, right? And lemma 11 is this one, that if a matrix A is invertible, if it's squared, invertible, then its columns form a basis of Rn. Okay, so we start off by assuming that A is invertible, so that means A inverse exists. Well, if you remember from the previous lemmas, if A inverse exists, that means we can use it as C such that CA is equal to IN. That means A has a left inverse, but from, let's see, this was lemma 6 or 7, that tells us that the columns of A are linearly independent. And similarly, the fact that A inverse exists means that there's a matrix D that can be used as a right inverse on I. And if you remembered from the previous lemmas 6 or 10, one of those, you could ask yourself to find that and remember that in case you need to use that. Exactly, 6 or 10 gives you that the columns of A span Rn. Well, now we have the columns of A are linearly independent and they span Rn, therefore they form a basis of Rn. Okay, so that's a handy thing to have. For example, let's say that you're given a set of vectors. They're all in R3 and you've got 3 of them and you're just wondering, do they form a basis of R3? Well, form A using those vectors as its columns. 1, 0, 1, minus 1, 1, 2, negative 5, 7, 2. Okay. Does A inverse exist? Well, remember, you have these graphing calculators, so you can enter the matrix A and then simply try to take its inverse using, as you recall, you can have a matrix A, you just refer to it, so that's just A sitting there, and then use that, the inverse button, press that. If it exists, it gives you A inverse. If it doesn't, it says something like A is a singular matrix. So that's a little bit of vocabulary. A being a singular matrix, that's a very old-fashioned way of saying kind of weird. If it's a singular matrix, then it's not invertible. Okay. So when your matrix is saying, your calculator is saying the matrix is singular, it's saying it's not invertible. Okay. So if A inverse exists, then yes, then since A inverse exists, then its columns form a basis of Rn. So you could say, then by lemma 11, if we're calling this set of vectors S, then S is a basis of R3. Okay. Another example of using this lemma, these ideas. Suppose you're given a matrix A inverse. Okay. Make sure that you can see there's negatives here on the 1 and on the 5. Without one of those, I think it actually becomes a singular matrix. Yeah, without this one, that becomes a singular matrix. So it's definitely an inverse of some matrix. Okay, so the question is, do the columns of A transpose form a basis of R3? So, do you remember all your lemmas, right? what do we have here? Well, let's see. A is invertible since A inverse exists, right? That's what it means to say the inverse exists, it's invertible. So therefore, the columns of A form a basis of R3. So you might go with that just by using Lemma 11. Right? That's not quite the question. The question was, do the columns of A transpose form a basis? Notice that we could have asked that same thing by saying not just the columns of A transpose, the rows of A. We could have put that in. Do the rows of A. We haven't talked about the row vectors a lot, but it's out there. Do the row vectors of A form a basis? Well, this, all we've got here is that the columns of A form a basis. But by Lemma 4 that you've had, A invertible exists implies A transpose is invertible. Do you remember what its inverse is? A transpose inverse by that lemma was equal to A inverses transpose. Remember, you could just switch those operations. Not kind of nice. So by Lemma 4, if we have A is invertible, then we have that A transpose is invertible. And by Lemma 11 again, implies the columns of A transpose form a basis. And in case this question was a little bit different, that would be the same thing as the rows of A form a basis. Well, that's a nice little fact, right? So if A is invertible, both its rows and its columns form a basis for, if it's an n by n, then for Rn.